I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see the machine learning based ECG signal analysis using Naïve algorithm and the machine learning based ECG signal analysis using Naïve is a simple and effective method for detecting heart problems by analyzing ECG signals. First, important features like heart rate, time between heartbeats, that is RR interval, and QRS duration are taken from the ECG waveform. These features are then given to a naive-Bayes classifier, which uses probability to decide whether the heart rate is functioning normally or if there is an issue like arrhythmia. This method is fast, easy to understand, and works well when even with the smaller data sets, making it useful for real-time heart condition monitoring. And also, this presentation provides a valuable insights and key points for researchers, serving as a comprehensive resource that streamlines their investigation process and offers a structured framework for exploring specific topics or methodologies. So we'll see one by one. First, the main objective of this presentation is to detect the abnormalities using ECG signal features and a naive-Bayes classifier. And this and the here we are using 20 data sets, that is 25 rows of data sets, we are using it, and each containing the ECG based features and binary labels. 0 is for normal and 1 is for the abnormal cases. We'll see one by one. And the data, these are all the data set features which we have taken it for our analysis. RR interval, this means time between successive heartbeats. That means the RR interval represents the time between two consecutive R peaks in an ECG signal. R peaks are the highest points in the QRS complex corresponding to ventricular contractions. Measuring the RR interval helps determine how regularly the heart beats. A consistent RR interval indicates a stable heart rhythm, while highly variable or irregular interval may suggest arrhythmias or other heart conditions. In ECG analysis, RR intervals are often measured in milliseconds and provide the foundation for calculating heart rate and heart rate variability. Next, HRV, heart rate variability. Heart rate variability, HRV, measures the variation in time between successive heartbeats derived from RR intervals. Rather than focusing on average heart rate, HRV looks at the beat to beat changes in timing, which reflects the heart's ability to respond to stress, exercise, or disease. A high HRV generally indicates a healthy autonomic nervous system and a good cardiovascular fitness, whereas a low HRV is often associated with the stress, fatigue, or cardiovascular vascular risk. HRV is a key non-invasive marker used in both clinical and wearable health monitoring. And the third feature is wavelet power, WP, energy content from wavelet transform. Wavelet power is a feature derived from applying a wavelet transform to ECG signals. Unlike traditional Fourier transforms, wavelets capture both frequency and time information. This is the main advantage of wavelet transform, making them ideal for analyzing non-stationary signals like ECGs. WP reflects how much energy or signal strength is present in specific frequency bands over time. Different types of heart activity, example, normal or abnormal, generate different energy patterns. So WP helps the classifier distinguish between healthy and diseased signals by quantifying these variations. Next, mean average ECG signal amplitude. This means of the ECG signal is the average amplitude value over a period of time. This value helps indicate the overall baseline level of the signal. In a healthy heart, ECG waveform has a fairly regular structure, so the mean remains within the certain range. Abnormalities such as elevation or a depression of the ST segment can shift the signal's average value. By computing the mean, the classifier gets a simplified but informative measure of the signal's central tendency, which can support deduction of certain heart conditions. Fifth one is the standard deviation. The standard deviation of ECG signal, it measures how much ECG signals varies from its mean. A higher standard deviation indicates a more fluctuating or erratic signals, which could be a signal sign of irregular heart rhythms or noise. Conversely, a low standard deviation might suggest a very stable or even flatline signal. These statistical features give insight into the variability and stability of the heart's electrical activity, which is especially useful when detecting events like ventricular fibrillation or arterial flutter. Next one is the skewness, that means signal symmetry measure. Skewness measures the asymmetry of ECG signal distribution around the mean. A skewness value closest to zero suggests a symmetrical signal, which is typical for normal ECG waveforms. Positive or negative skewness indicates that the signal has more pronounced peaks or dips on one side, which may correspond to abnormalities like enlarged QRS complexes or distorted T waves. Including skewness as a feature allows the classifier to deduct such structural distortions in the waveform shapes. And we are using the labels 0 and 1 target classes. The label is the target output used for classification. It represents whether ECG signal belongs to normal heart rhythm, means 0, or an abnormal condition, means 1, such as arrhythmia or other cardiac issues. During the model training, each feature set is paired with a label to help the naive based classifier learn the underlying probability distributions. During testing or real time use, the model uses the learned probabilities to predict whether a new ECG signal indicates a normal and abnormal heart conditions. So, this is the 25 row data set we have taken. The full data set for this example, we have taken 25 rows. This data set contain 25 rows, each representing the ECG signal samples with extracted features like RR interval, HRV, WP, wavelet power, mean, standard deviation, and skewness. Each row also include a label indicating whether the signal is from a normal or abnormal. Normal means 0, abnormal means 1 heartbeat. These features are used to train and test a naive based classifier for accurate heart abnormality detection. Next, data split. Total records we are using 25, and here the training sets we are using the data set used for ECG based heart abnormality detection. In this example contains a total of 25 records, each representing a unique ECG signal samples. Each record include various extracted features such as interval, as I've said, interval such as RR interval, heart rate variability, wavelet power, mean, etc. The small and structured data set is suitable for implementing and testing a basic naive-based classification model. So here we have this 13 rows we are using it for training. The remaining 12 rows we are using it for testing. So the training set we are using the training set. The first 13 records, rows 1 to 13, are used as the training set. During training, the model computes the mean and the variance of each feature for both classes, normal and abnormal. These statistical values are essential in naive Bayes, which assumes each feature follows a Gaussian distribution and uses this information to estimate the likelihood of sample belonging to each class. The training data allows the classifier to build a probabilistic understanding of ECG features associated with heart rate. Testing set. Rows 14 to 25, we are using this, we have given in a different color. The remaining 12 records, rows 14 to 25, used to form the testing set, which is used to evaluate the model's performance. For each test sample, the trained Naïve-based model calculates the posterior probability of the signal being normal or abnormal using the means and variances learned from the training set. Based on these probabilities, the model predicts the class label. Comparing these predictions with the actual labels helps the measure the model's accuracy and reliability in identifying heart abnormalities. And we are calculating the mean value. Mean value is mu naught. So we start by taking the so here training set RR interval. Here we are splitting into this 13. We are splitting into normal and abnormal case. First we are considering zero label. So 8, 7, 8, 1 and 8, 8 and another value is 9, 6 like that 8, 6. So here 8, 9. For that we are separately finding out the mean value for 0, that is normal label 0. If you are finding out for each value, you are finding out 8, 7, it just you look into the table and you can able to find out. Similarly, HRV, wavelet power, mean and standard deviation, skewness. And similarly, for calculating the variance, the formula of mu means you have to sum up all the values divided by 7. And similarly, and mu calculation for mu naught square means label 0, the actual value minus whatever we found out the mean value. The first 8.87 minus 0.8643, and similarly you have to call plus sum up all the values. 81, this 0.81 minus this value, plus 0.88 minus this value, square divided by 7. This is the variance value. The previous one is sum up divided by total number of values. Similarly, for HRV, WP, mean, standard deviation and skewness, we are finding out the variance. We are finding out next. Next we are going for the testing phases. So here the testing we are considering from 14 to 25. The remaining 12 records, rows 14 to the testing set, which is used to evaluate the model performances. All you know that for each test sample, the trained Naïve-based model calculates the posterior probability of the signal being modeled as normal or abnormal using the means and variance learned from the training set. Based on these probabilities, the model predicts the class label. Comparing these performances predictions with the actual labels helps measure the model's accuracy and reliability. So 14.3 row, we have to calculate the probabilities by using this formula. 1 divided by root of 2 pi sigma square into e to the power minus x minus b the whole square divided by 2 sigma square. This is the Gaussian distribution which is used for finding finding the test values. And multiply all 6 probability each class to get the likelihood of 0 and 1. Multiply each likelihood class by prior 7 by 13. Zeros, how many labels are there? 7 labels are there. Zeros, 1, 2, 3, 4, 5, 6, 7. And ones are, how many ones? 6 ones are there. So 17 plus 6, 13. Comparing posterior 0 and posterior 1, we have to choose the higher one for the predicted label. So the Naïve-based prediction pipeline, we start by taking the test row, the collecting all 6 features such as RR interval, HRV, wavelet power, mean, standard deviation and skewness. For each feature, we calculate the probability of that given class as normal or abnormal using the Gaussian probability model. These probabilities are multiplied together to get the overall likelihood of each class. We then multiply each likelihoods by the prior 7 by prior probability 7 by 3 for normal, prior 0, prior 1 for the abnormal. Finally, we compare these two posterior values and assign the label of the class with the highest probability as the predicted outcome. So this is what, if posterior value is greater than posterior 1, we are calling it as the predicted value 0. Otherwise, posterior 1 is greater than posterior 0, we are calculating it as the 1. Value it as equal to 1. In the same case, we have a detailed discussion we are given in this. The same whatever we have discussed, all the values we are going to take, and we are finding out the likelihood values for similarly for class 0, and also we are finding out for the class 1. And from this we are coming into the conclusion the posterior value is 1885.4 and this value is 1471. Which one is higher? The posterior 0 1 is greater than posterior 0. The predictor values, whichever the value is giving the highest value, that we are going to take into account. So the value will be later be compared to the posterior for class 1 to determine the predictor value. In this case, the predictor value is the 1. The same calculation, the formula we are applying to it, e power minus mu minus sigma, this the same formula here, whatever e power x minus mu the whole square divided by 2 sigma square, we are substituting and for each values, and we are multiplying with the posterior 0 for multiplying with the 6 by 13, posterior 1 is multiplied with the 7 by 13. So here the class 1 we are finding out from this posterior 1 is greater than posterior 0, predicted value is 1. Similarly for rows 15, 16, 17, 18, in this case the predicted is 0. Whatever it has been given in the table is also 15. 0, okay. So it matches. We are calling it as, if it has been matching, we are giving it as predicted is putting the right tick mark. Row 16 also tick mark predicted 1 and actual given is also 1 and row 17 predicted is 0 and the given is also 0 and row 18 we found out 0 but actual is 1. So we are calling it as the false positive. And similarly 19 predicted is 0, given is also 0, right. 20 predicted is 1, given is also. So if you are having the doubt, you have to look into the table. 20, what is the value? 1 is given. What we found out, the value is also 1. We are giving it as a right tick mark. But in this 21, predicted 1, given is 0. So this is the false negative and this is false positive. 23, 24 and 25, all the values we are correctly predicting. So in this case, 14 to 15 only testing phase. So the actual is 100 like this and predicted is true. If both are 1, true positive, both are 0, we are calling it as true negative. Both are positive, true positive, both are 0, true negative. 1, 0. Instead of getting 1, we are getting the 0. So false negative. Here, this we have to write. If we are not getting, we have to get this negative but false negative. This is true negative, true positive, but here we have to get 0 instead of getting 1. 1 means positive, but what we have to write here? False positive we have to write. Here we have to get 1 instead of getting 1, we are getting 0. So false negative, true negative, false, true positive, true negative. All the values we have to count. How many true positives are there? 1, 2, 3, 4. How many true negatives are there? 1, 2, 3, 4, 5. 5 values are given. So this we have to write. Here true positive is 4. False negative, how many are there? 1 and 2. False positive is 1. False positive is 1 and true negative is 5. So in order to arrive this confusion matrix, you have to carefully calculate all the values. This confusion matrix only will give us a final performance result. So we have to be very much careful in calculating these values. Okay. And after performances matrices are accuracy, prediction, recall, and F1 score. Accuracy means it measures the overall correctness of the model by calculating the proportion of correctly predicted samples, both positive and negative, out of the total predictions. In this case, the model correctly identified 4 true positive and 5 true negative values. So we have found out true positive 4 plus 5 divided by total values. All the values we have to sum up. 4 plus 2, 6, 7, 7 plus 5, 12. So 12, if you are putting 75%, you are getting. The accuracy is 75%. Next, precision. Precision indicates the percentage of positive predictions that were actually correct. It helps us understand how many of the samples predicted as abnormal truly had heart abnormalities. Here, the model predicted 5 samples as abnormal, out of which 4 were correct and 1 was incorrect, false positive, and precision is given by the formula true positive divided by true positive plus false positive, 4 divided by 4 plus 1. So 80 percentage we are getting. So this shows that 80 percentage of the abnormal predictions were accurate, which is important in medical context to minimize false alarms. Next, recall. Recall measures the ability of the model to correctly identify all actual positive cases. Out of 6 true abnormal cases, the model correctly predicted 4 and missed 2 false negatives. The formula is given by true positive. Here, true positive, false positive is the precision, recall is the false negative. 4 divided by 4 plus 6. So we got 66.67. This means the model was able to detect approximately 67% of actual heart abnormality cases. Higher recall is crucial in healthcare to ensure that serious conditions are not overlooked. Next, final important measure is the F1 score. The F1 score is the harmonic mean of the precision and recall, providing a single metric that balances both. It is especially useful when dealing with the imbalanced data sets using calculated precision, that is zero point 0.8, and also recall is 0.667. The F1 score is given by formula 2 into precision and recall divided by precision plus recall. By substituting all the values, we are getting 0.7273 or 72.73 percentage. This F1 score reflects a good balance between correctly identifying abnormal cases and minimizing false alarms, making the model fairly robust for ECG based abnormality detection. And what is the insight? So we have seen so many calculations. What is the insight of this algorithm? The Naïve algorithm classifier has been effective for ECG signal analysis, especially under assumption that features follow a Gaussian normal distribution. Even with the relatively small data set, the model was able to provide meaningful insights when the features were carefully selected and represented relevant physiological patterns. Among the extracted features, RR interval, wavelet power, and skewness emerged as the most influential in predicting heart abnormalities. This all you know that these features captures essential aspects of ECG waveform such as timing between beats, energy concentration, and waveform shape, making them critical for distinguishing between normal and abnormal heart activity. This highlights that even simple probabilistic model like Naïve can perform well when supported by domain relevant and statistically informed features. Next, coming into the conclusion, the ECG based signal classification using the naive base gives interpretable predictions. How means one of the main advantage of using naive based classifier for ECG signal classification is its simplicity and interpretability. Unlike complex black box model, naive base provides a transparent, mathematically grounded predictions by computing the probability of each class based on feature values. This transparency makes it easy to understand which features like RR interval or wavelet power contributed to particular classifications. For healthcare professionals and researchers, this interpretability is critical as it helps in validating the system's decision and ensures the clinical trust in the automated diagnostic process. The second performance is the effectiveness of the naive base model heavily depends on the assumption that the input features for each class follow distinct Gaussian distributions. When there is a clear separation between feature distributions for normal and abnormal ECG signals, the classifier can compute accurate likelihood and make reliable predictions. However, if the feature distributions overlap significantly, the model may struggle to distinguish between classes, reducing its performances. Thus, feature engineering and proper data pre-processing, that is normalization, outlier handling, play a vital role in enhancing the model's reliability and accuracy. And the third one is due to its lightweight computation and fast decision making ability, the naive Bayes algorithm is well suited for real time applications such as seizure reduction or continuous cardiac monitoring. It requires minimal computational resources and provides quick predictions, making it ideal for deployment in wearable devices or embedded health monitoring systems. When integrated with ECG sensors, it can assist in early detection of abnormal heavy activity, heart activity, alerting patients or healthcare providers immediately, which is crucial for timely intervention and improved patient outcomes. Hope this interesting topic everyone understood. So this presentation will be very much helpful for the researchers who are all doing the research in this area. The remaining things we'll discuss deeply in the next lecture. Thank you.